Hello viewers, in this video I'm going to be showing you how to solve problems that are related to application of first order differential equation. So this is engineering mathematics and we are going to solve problems on application of first order differential equation. We already know that there are solutions to first order differential equations such as the use of direct integration. We have the use of linear equation, we have homogeneous equation, we have exact equation, we have Bernoulli's equation. So we've done all of that, and now we want to see how we can actually apply those equations in solving real life problems. So this is one of it. So we have the rate at which a body cools is proportional to the difference between the temperature of the body and that of the surrounding A. If a body in A is at 25 degrees Celsius, will cool from 100 degrees Celsius to 75 degrees Celsius in 1 minute. Find the temperature at the end of 3 minutes. So this is a typical question of how a body cools and the difference between the temperature of the body itself and that of the surrounding A. So first we are going to establish a formula that will relate the temperature of the body and that of the temperature of the body that is cooling and that of the surrounding A, and then from there we can solve the question. So let's say solution. Let me take solution here. So the first thing is we say let the temperature of the body be T degrees Celsius. So the temperature of the body will be represented by temperature in degree Celsius, and we are told that the temperature of the surrounding A is 25 degrees. So we say temperature of surrounding A, which is equal to 25 degrees. So once we've taken that down, all these ones are initial conditions that we are going to consider later in the question. But first we have to establish a relationship between temperature of the body and that of cooling. Now if we look at this question, we are told that the rate at which a body cools is proportional to the difference between the temperature of the body and that of the surrounding A. So that implies that the change in temperature, because this is happening with respect to time, so we say that the change in temperature with respect to time, that is d temperature over d time, is proportional to the difference between temperature of the body and that of the surrounding. So temperature of the body is T degrees, so this would be T minus that of the surrounding is 25. So we can put this in brackets, okay? And then we can say where this big T is temperature and then the small t is time. So we've been able to, from this question, show the relationship between the rate of change of temperature with respect to that of the body and the surrounding. And now this is sign of proportionality. And so if we introduce a quality sign here, we also introduce a constant. That is the practice. So we can call this equation 1. So if we introduce the quality sign into equation 1, if we replace the sign of proportionality with the quality sign, we introduce a constant. So we have the T temperature over the T time will be equal to K into T minus 25. Okay? So since we've introduced a quality sign, we now introduce a constant. Now, having done this, we now look at the question. In this question, we can now use method of separation of variable, which is part of solution to first order differential equation, to solve this. So we said, okay, this is equation 2. I'll now say by using method of separation of variable. So by using this method of separation of variable, what it implies is we are going to take temperature to where temperature is, and then this time will go to the right hand side where the constant is. So we've separated the temperature will come here because this is temperature, and time will move down here. So in order to achieve that, first we have to say multiply both sides of equation 2 by 1 over t minus 25. So this is equation 2. So we are going to multiply both sides by 1 over t minus 25. And so if we implement this mathematical statement, we are going to have, for the left hand side, we are going to have dt over this times 1 over t minus 25 equal to, and then in the right hand side of the equation, we are going to have k into t minus 25 times 1 over t minus 25. And so if you look at this, we can cancel out this from here, and this will go. And so our next equation is going to look like this. From the left hand side of the equation, we are going to have, from the left hand side of the equation, let's take this, we are going to have 1 over t minus 25 dot, the dot means multiplication, dt over dt with respect to time, dt time, equal to, and what we are going to be left with in the right hand side of the equation will just be k. So we have k here, okay? And so we can call this our equation 3. Let's call this equation 3, okay? Now we also have to eliminate this from here so that you can go to k, to the right hand side of the equation rather. So in order to achieve that, we can say multiply both sides of equation 3 by the time, that is the t, the small t. So we say multiply both sides of equation 3 by the time. So when we implement this mathematical statement, we are going to have 1 over t minus 25 dt over this times dt will be equal to this for the left hand side, and then for the right hand side we have k times this. So if you look at this, this will cancel out, and so for the left hand side you are going to have 1 times dt will give us dt, this is 1, this is 1, all over t, 1 times t minus 25 will be t minus 25. This will be equal to, if we say k times dt, to give us k dt. So we can call this equation 4. So looking at equation 4, we can now say, okay, we've been able to separate our variable successfully in equation 4. We can now see that the temperature and t minus 25 is standing in the left hand side, while we have k and the time on the right hand side of the equation. So having gotten this, we can now integrate. Having gotten this, we can now integrate. So we say integrating. Okay, even before we do that, let's look at it from this angle, that dt over t minus 25 is the same thing as saying 1 over t minus 25 dt. This will be equal to k dt of time. So this is equation 5. So let's say integrating equation 5. So we integrate equation 5. So in integrating equation 5, we are going to have integral of 1 over t minus 25 dt equal to, this is a constant, so we bring it out and integrate the small t, or the time. So we have the constant integral of the small t. So we've gotten to this point now. So having gotten to this point, this is 1 over, so if we integrate 1 over minus 1 over t minus 25 is going to give us ln into t minus 25 equal to, if we integrate dt, we are going to have, okay, if we integrate dt, we have t, and then we add the constant of integration. I think I should erase this and then take it down to this other end. So if we integrate this, we are going to have ln, that is a standard integral of t minus 25, equal to, we have k here, so we write k. If we integrate dt, we have t, and then we add the constant of integration. We can call this equation 6. Okay, so having done this, you can from this point bring in your boundary conditions, but let's make this equation a bit simplified. Okay, so in order to eliminate ln here, we introduce exponents. So introduce exponential or exponent. So when we introduce exponent ln into t minus 25 equal to exponent kt plus exponent c. So we introduce exponent. The essence is to eliminate the ln at this point. So we know that exponents and ln will cancel out, and so we are left with t minus 25 equal to exponent kt plus exponent c. I want to further simplify this equation, and so I can say let exponent c equal to a. So if exponent c is equal to a, then if we call this equation 7, if exponent c is equal to a, then equation 7 will now become t minus 25 equal to exponent kt dot a. Now it is dot, this is indices, because it's positive here, it will be multiplication, because this is the same thing as saying exponent kt plus c, or this is the same thing as saying exponent kt dot exponent c. This is what it means, so that you can now have exponent kt plus c. So that is it. So we have dot a. So this will be equal to t minus 25 equal to a exponent kt, and we can call this equation, let's call this equation 8. Okay, so this equation is very important because this is what defines, the linear relationship between temperature of the body with time. So at this point, we can now bring in our boundary conditions So we now have to introduce boundary conditions. We have to introduce our boundary conditions. So coming back to the question, we have that if a body in A is 25 degrees, will go from 100 to 75. So what this implies is that at T, time equal to 0, at big T, that's the temperature of the body, will be what? 100 degrees. What this implies, if a body in A at 25 degrees will go from 100 degrees Celsius to 75 degrees in 1 minute. So at T equal to 0, the temperature of that body will be 100 degrees Celsius. But at T equal to 1 minute, we are told that the body cooled from 100 degrees Celsius to 75 degrees Celsius at 1 minute. So this implies that at T equal to 1 minute, the temperature of the new body, or the body again, will be what? 75 degrees. So these are our own boundary conditions that we are going to consider while solving this problem. So now let's call this boundary condition 1, and we call this boundary condition 2. Okay, so substituting boundary condition 1 into equation 8. So we say substituting boundary condition 1 into equation 8. So this is equation 8. We know that our big T is 100 degrees, so we are substituting boundary condition 1 into equation 8. And then we have minus 25 equal to A exponent K. But at time T, boundary condition 1 is 0, so this will give us 0. Okay, let's rub this off. Okay, so 100 minus 25 will give us 75 minus, this is A, exponent K times 0 will give us 0. So we are going to have, okay, this will be equal to A exponent 0. But exponent 0, if we check in our calculator, is 1. So this will be 75 equal to A times 1. So this 75 equal to A. So what it implies is our A is 75, or 75 equal to A. So we can call this equation 9. So we can further say substituting boundary condition 2 into equation 8 again. So we are going to substitute this boundary condition 2 into equation 8. The essence is for us to decide. We've gotten A, so we need to have the value of the constant K, so that we can actually find what happens at the end of 3 minutes. So substituting boundary condition 2 into equation 8, our T for boundary condition 2 is 75, so we have 75 minus, this is 25, equal to A is now 75, and then exponent K into our T for boundary condition 2 is 1. So this will be 75 minus 25 will give us 50 equal to 75 exponent K times 1 will give us K. So note we are looking for K. So we have to divide both sides by anything that is close to K. So we say divide both sides by 75. So this will give us 50 over 75 equal to exponent K. So let's use our calculator to find the value of 50 divided by 75. So 50 divided by 75 is 2 over 3, which is the same thing as 0.666. So we have that 0.666 equal to exponent k, or we can say exponent k equal to 0.666. Okay, now, but we know that we are looking for exponent for k rather, not exponent a, k. So in order to eliminate the exponent, we introduce what? Ln. So we can say ln exponent k equal to, sorry, so we introduce, okay, let's call this equation 10. So we say introduce ln. So we said ln exponent k equal to ln into 0.666. Okay, so we know that ln exponent k will cancel out, so we are going to be left with k equal to ln into 0.666. so k now will be equal to, let's find the value of ln 0.666. So this will give us minus 0.406. So the value of our constant now is minus 0.406. What does this imply? This is the constant of proportionality between the temperature of the body and that of the surrounding air. So with this constant, we can actually predict the value. Okay, we can find the temperature at any given time with this value of constant, and with the value of this constant for this particular question and the value of this A, we can actually predict the temperature of this body at any given time t using equation 8. So in our question, we are asked to find the temperature at the end of 3 minutes. So we are going to use this constant, the value of this constant, and the value of A. We impute it into equation 8 to determine the temperature at the end of 3 minutes. So let's take this. So we say at t equal to 3 minutes. So at t equal to 3 minutes, we are going to use equation 8. So we have t minus 25 equal to a exponent kt. This is equation 8. So we are looking for this temperature because they said find the temperature at the end of 3 minutes. So we can say that t, we move 25 to this, the right hand side, so this will be equal to 25 plus, because 25 is minus here, so when it crosses the sign of equality, it will be positive. So 25 plus a exponent kt. So the temperature T will be equal to 25 plus, we know that A is 75, so 75 exponent minus K is minus 0.406 into our time is what? 3 minutes. Our time is 3 minutes. So this will be equal to 25 plus 75 exponent minus 0.47 multiplied by 3. Let's see what that will give us. 0.406 multiplied by 3. That will give us, so this will give us minus 1.218. So this will be equal to 25 plus 75 x. Okay, so we now find the value of exponent minus 1.218. So So for you to find your exponent, if you're using this kind of calculator, you take you shift and then lane minus 1.28. Is that correct? Okay, 1.218. And so that will give you 0.295. So we can now say 75 times 0.295 times 75 times 0.295. So this will now give us 25 plus 75 times 0.295 is 22.125. So we can take 0.13. We can take 0.13. So at this point, we can now add, say, 25 plus. So this will give us that our temperature equal to 47.13 degrees Celsius. So what this implies is that the temperature of this body, considering this question, at 3 minutes will be 47.13 degrees Celsius. That's what it means. And so with this formula, with this equation, using the value of constant and that of A, which is this and this, you can actually predict the temperature of this body at any given time. Thank you.